All right, we finally made it to chapter 21, podcast 9, which is all about electrolytic cells. So we're going to figure out how do electrolytic cells differ from voltaic cells, and then how can we use that to our advantage chemically, and what is the math that we need to kind of sort out when it comes to electrolytic cells versus a voltaic cell themselves. So let's dive right into that topic. So a voltaic cell was a spontaneous redox reaction, right? Whereas an electrolytic cell, you have a non-spontaneous reaction, but we are forcing that reaction to take place by applying an external force to our reaction system. And the way that we usually do that is by an external voltage by a battery. All right. Now the battery itself is a voltaic cell, but it is forcing an electrolytic cell to work by making a non-spontaneous reaction take place. So what we say is that our battery is pumping electrons into our system. If we look at our picture over here to the right, we have our battery. We have the anode part of our battery is going to pump electrons out, and those electrons that are being pumped out are going to enter at the cathode part of our electrolytic cell, where they're going to be dipped into some sort of an aqueous solution. Here I've got some sort of a metal. The metal is going to react with those electrons and plate on that cathode. All right, then, right, when that happens, the electrons are going to keep transferring over. They're going to come over here to the anode part of our electrolytic cell, where they're going to then leave the anode, right? They're always traveling anode to cathode. It's just that we have two different cells here. One of them is a battery, a voltaic cell. One of them is our electrolytic cell. Those electrons are going to exit the anode and going to enter back in to the cathode part of our storage battery there. So the battery itself is forcing electrons into our system, and that is then making the reaction take place, right? So we've got our metal plating over here, and over here we've got some anions, right, where those anions have extra electrons that they can then transfer into that anode. Right, we might have heard of this as something, right, the terminology before this is called electrolysis. And so one thing that we do for electrolysis is that we put electrical current through water. If we put electrical current through pure water, we can separate water into hydrogen gas and oxygen gas. We can actually collect the hydrogen and the oxygen gases separately. But water itself, if you have a glass of water, that's not going to just separate out into hydrogen and oxygen. We have to pump that electricity through it, right? We could hook up a battery and run it through the water to do that. So that's the basics of how an electrolytic cell differs from a voltaic cell. When we desire to work calculations using electrolytic cells, we are always going to need to eventually use what we call the quantitative relationships between the number of moles of electrons and the number of moles of metal that are produced. Okay, so, right, these equations are always going to be used at some point. So what we need to see is our top equation there, right? We have silver cations, right, are going to react with 1 mole of electrons to produce 1 mole of silver solid. All right, now notice that silver cations are always +1, right? Silver is one of those like odd transition metals that always has the same oxidation number. It happens to be +1. All right, so it's going to take, if you had 1 mole of silver cations, it's going to take 1 mole of electrons to produce 1 mole of silver. So another way that we can kind of say that is that 1 mole of electrons are needed per 1 mole of solid silver that we're going to produce. So we can use this as a conversion factor. All right, now the next one down is like if I have copper 2. Notice that it's going to, in order to convert each copper is +2. In order to make that copper solid and have a charge of 0, it's going to take 2 electrons. Right? Well, if we've got our copper 2, and it takes, if we have a mole of copper 2, it's going to take 2 moles of electrons to produce 1 mole of copper. So we're going to need 2 moles of electrons per 1 mole of solid copper produced, and so on. So if I need to know the number of moles of electrons in order to produce 1 mole of solid metal, we can look at the charges that are present, right? So I'm sure that we can see the pattern here with our gold 3. It's going to be 3 moles of electrons for every 1 mole of gold, right? And so on. We are going to need those relationships when we work our electrolytic cell problems. So keep this in mind. We're going to see it as we work a problem in a few slides before the end of this PowerPoint is over. Along with the relationships that we saw between the number of moles of electrons that are needed to convert moles of ions into metals, right, we also need to take a look at the fact that we need to introduce some electrical units as well. So far in this chapter, the only thing that we've talked about has been something we call voltage, right? And that voltage drove the flow of electrons. But there's other things when it comes to electrical units. One of them, our top one there, is the charge of something. All right, so the charge of something, we give the units of coulombs, which we give an uppercase C as the symbol for coulombs. All right, notice that it says that 1 mole of electrons has a charge of 96,480 coulombs. All right, notice that 96,480. That is Faraday's constant, right? We've seen that before. That's where that comes from. Well, this is saying that we have 2 values that are equal to each other. So remember, we can use that as a conversion factor. That 9.648 times 10 to the 3rd coulombs per 1 mole of electrons, or we could write that as the inverse of that, 1 mole of electrons per 9.648 times 10 to the 3rd coulombs, depending on what we're trying to get. Another electrical unit that we might need is current. Current is given in amperes, and those are given the symbol of A, as we see there. And 1 ampere happens to have units of 1 coulomb per second. So we're going to be able to convert coulombs and amperes within each other. We're going to see that when we work problems, right? Because we're going to worry about time, right? We're going to say, how long have we been, I'm not having a good job of writing, how long have we been doing electrolysis? And we need that time frame in there. All right, and then lastly, we have our electrical energy on here, which we usually are going to say is in joules, or of course, we could do this in kilojoules. We could also say that we could have kilowatt hours, right? Kilowatt hours. This is the English system. So only awesome countries like the United States and powerhouses like Burma still use the English system, like kilowatt hours. So we probably won't stumble across that one, but a kilowatt hour is 3.6 times 10 to the 6 joules, or 3.6 times 10 to the 3rd kilojoule. Right, but the units for a joule are coulombs times voltage. All right, and so that will be helpful for us a little bit later. We need to pay attention to those units, but we're going to work a sample problem. We're going to see all of these units kind of coming into interplay with each other. If you can do the sample problem that we do, then you can do any electrolytic cell problem. There's sometimes like one little step at the end that's gonna like, trip you up, but I'm gonna show you the basics for all electrolytic cell problems, and then you might have to do one last step on a problem later on. But we'll see how that works out in just a couple slides from now. Here we have a table of different electrical units. Right, so we can talk about these things where we've seen that the charge is given in units of coulombs. Right, notice that coulombs also have units of amperes times seconds, which is also joules per volts. Our current is in amperes, and an ampere is coulombs per second. Right, our potential is in volts. Right, volts are what we have dealt with all throughout this chapter up until this very final podcast. Right, so any of the stuff that we did in the first 8 podcasts, we were always talking about the voltage of things. Power is in watts or in joules per second. We will probably not do anything with power or with kilowatt hours there, so don't pay attention to that. But this is a good table to come back to. If when you're working through a problem you don't remember all of the units and how they kind of intermingle with each other, then this is a good thing that you can kind of flip back and just double check and say, oh yeah, that goes with this. That's voltage times coulombs, and a coulomb is amperes times seconds. So a joule is really volts times amperes times seconds, and so on. So we can actually kind of figure that stuff out by looking at this table. All right, from that, we can then work a sample problem. And like I said, almost all these sample problems are going to be worked the same way. So let's work through it, and then we'll do our last step so you can see how they can all kind of differ at the very end as well. All right, so our sample problem 21-8, dealing with electrolytic cells, reads that we have a solution that has a metal ion. The only thing we know about the metal ion is that it is M and it's 2+. It says that it is electrolyzed by a current of 7.8 amperes. After 15.5 minutes, we have 2.39 grams of the metal plated out. All right, so that means that we have 2.39 grams of the metal has been converted from cations into solid metal. And so A asks, how many coulombs are supplied by the battery? So amperes are in coulombs per second. So we need to say, all right, I have amperes in the problem, and I have time in our problem. All right, so I can really say that amperes are 7.8 coulombs per second. And if I want to know the number of coulombs, we could multiply this by the time in seconds, and that would just leave us with coulombs. So that's what we're going to do for part A. But we have our time as 15.5 minutes. We need to convert that into seconds. So we know that there happens to be 60 seconds per minute. So we find that 60 times our 15.5 is 930 seconds. So now we can plug that in. So we've got our 7.8 coulombs per second times 930 seconds, and we get 7,254 coulombs. All right, which is 7.3 times 10 to the third coulombs, if we wanted to put it in right number of sig figs. All right, part B of the problem. All right, says assuming 100% efficiency. All right, 100% efficiency. What that means is that every single electron that is put through our system is used to convert a cation into the metal. none of the electrons flow through and just keep on flowing through. They all are going to react with cations and turn them towards becoming metals. Now it takes two of them to convert our M2 into a metal, but it's not like one of them is going to pass through and another one's going to react with the metal. Both of them are going to react with that to turn it into the metal. So all of them are working towards converting cations into metals. All right, it wants us to know what is the metal. So I'm going to get rid of this because who knows what slide number this is. So, and then moles of the metal as seen on some previous slide. I don't know what slide it is because I've changed them around whenever I've done this as a podcast. So what we want to do then for this problem is we're going to start with coulombs. All right, we are going to convert coulombs into moles of electrons. We are then going to convert that into moles of our metal. All right, so let's start with that. We have our coulombs from part A. 7.3 times 10 to the third coulombs. If I want moles of electrons, I'm going to say that there are 1 mole of electrons per. All right, we are going to use our Faraday constant, right? Our 96,480 coulombs. Now we want to find the number of moles of metal. All right, so right, we have to see up at the top. This is M2 plus. So what that really means is that I'm going to get 1 mole of metal. But to get a mole of metal, it's going to require 2 moles of electrons. Right? That 2 are M2 plus. So we are going to end up with 0.0376 moles of our metal. All right, so what I'm going to tell you is that almost every problem that's going to deal with electrolytic cells is going to want you to get the moles of metal. Heck, that's usually where you're going to even stop. Now, every once in a while, you might have to take this a step further, which we are going to do here because I want to know what that metal is, not the number of moles of metal. All right, so when you have an electrolytic cell, right, what you're usually going to do is you're usually going to convert amperes to coulombs, to moles of electrons, to moles of metals, just like we did in these steps so far. Right? You're going to do that almost 100% of the time, and then you might have an extra step to do. All right, here we have, all right, moles of our metal, but it really wants to know, right, what the metal is. Well, I can figure out what the metal is if I know grams per mole of the metal, and then I can look up what it is on the periodic table. Well, I know that we also made 2.39 grams per 0.0376 moles. And so we're going to get 63.56 or 63.6 Spacer 63.6 grams per mole. If you look at a periodic table and find the one that has the molar mass closest to that, the answer is going to be copper. And that was our final answer then. So here we had one more step to do just to make sure that we could figure out what the metal was by figuring out the molar mass of it and then looking at the periodic table. But again, most problems you're going to have to go through these steps one way or the other. So make sure that you look this over and can do those steps. So you might wonder to yourself, what in the world would I use an electrolytic cell for? Well, if you've ever heard of something like, a silver-plated ring or gold-plated jewelry or something like that, what they've done is they've taken a cheaper piece of metal. So here I've got a spoon sitting in there, and we're going to pump some electrons into this, and we're going to convert, in this case, some silver, which is here, and we're going to convert those silver cations into silver metals where they're going to plate over there on the cathode side. Well, they're going to plate on that spoon. So we've got a cheap piece of metal, and we're going to have a thin film of silver that's going to plate over that by using an electrolytic cell, right? So we're going to pump electrons in from the anode of our battery into this cathode here, and then electrons are going to flow back out of the anode of this back into the cathode of the battery there. But we're going to be able to plate like a thin, lame little layer of it. And so it looks like on the outside it's a nice piece of silver, whereas really you can save a lot of money because only the outside is silver and the rest of it is just a cheaper metal that was easy to get. So that's the application of actually doing electrolytic cells. Again, go back and double check that you can work that problem that we just did, because I love putting an electrolytic cell problem on exams, even though it's a short section compared to how much there was for the rest of this chapter in our voltaic cells. Make sure that you can work one of those. And that concludes chapter 21. All right, I'll see you guys for the next chapter.